Okay, here's Unit 3. In Unit 3, we start our dimensional analysis, which is mainly the majority type of math that we do here in chemistry class. But before we get to our dimensional analysis, let's go ahead and start off here with our scientific notation. I know you've been taught this before, so it should be hopefully a quick, easy review for you. And the reason why we start off with the scientific notation is because we deal with very, very, very big numbers for very little things, right? So imagine like one atom, okay? One tiny atom. Imagine how many tiny those little atoms it takes to make up any object, okay? And because it takes so much, these numbers are so huge that we use a lot of scientific notation in this class. Also, I want to make sure that I go over how to type in the scientific notation into your calculator. And let me see. Yes, it looks like it's going to turn on. So yay. Okay, so we'll do that in just a moment. So make sure you have your calculator out ready to go. We're going to be using this for this unit and pretty much the rest of the school year, okay? You're going to need a calculator that you can do exponents with, okay? And not necessarily, we don't need it because of the graph or graphing process. We need it because of the exponents, okay? So we will look at that in a little bit. So let's start off with scientific notation. Scientific notation, it says here, is a really quick way to write really big and really small numbers. Now, there are a few rules for scientific notation. Number one, to be a proper scientific notation, the number must be written with one number to the front of the decimal or to the left of the decimal. Okay, only one number to the left of the decimal. Okay, now it must be between the number 1 and 9. Okay, next one, and multiply by the power of 10, which indicates the number of places that the decimal needs to move. It says here, if the number is greater than 1, the exponent's going to be a positive number. If the number is less than 1, then the exponent will be a negative number. Okay, positive number, negative number. The number 1 through 9 needs to be to the left of the decimal. So this number right here cannot be a 10, it cannot be 11, it cannot be a 12, it cannot be a 0. That does not work. Here's my decimal. Okay, the remaining numbers have to go behind it. So if it's 6 more actual numbers, and I mean numbers, not zeros. If there's zeros in between two numbers, for an example, 7.10004, we would have to keep all of those values there before we get to the times 10, okay? So here's a couple of practice problems right here. 2, 20, and this number, huge number, right? 0.2, 0.000002. Okay, it's very, very small number. Okay, so those are examples of numbers that are greater than 1. And here are examples of less than 1. Okay, so if it's greater than 1, like here are 3 examples, then we're going to have a positive exponent. For an example, 2. Where's the decimal? Because we need to know where the decimal place is first before we start our practice problems. Okay, our decimal is behind the 2. On number 2, the decimal is behind this 0. And on number 3, the decimal is all the way over here to the end, right? So we actually do have a decimal. They're just invisible. And we need to make sure that we remember that. So if I need to create or put this number into scientific notation, I need to first ask myself, how many places is the decimal going to move? Well, how many places is it going to move? It's going to move 0 places. Why? Because there's right here one number already to the left of the decimal. This has 2 numbers. That's not going to cut it. And this has 3, 6, 9 numbers to the left of the decimal. Okay, that's not going to cut it. But this one, though, is one number already to the left of the decimal, meaning that I can't move the decimal. Could I put this in scientific notation? I like this example to start off with. Okay. Yes, I can put this number into scientific notation. 2. Some teachers prefer you to put 0.0, okay, even though there's nothing else behind this, which is okay. If you put 2 by itself, that's also okay. Times 10. Now I need to know what power am I going to use. Now my power is going to be a positive number because that's what it says over here. But you ask yourself, how many places did I move that decimal? I moved it 0 places, okay, to the 0 power. And that is a valid scientific notation number right there. All right, so the number 20, I need to move that number 20. I'm going to move this decimal over here 1 place. So 2.0 times 10 to the first power. Again, positive exponent. Why? Because my number is greater than 1. Next one. 2. 1, 2, 3, 4, 5, 6, 7, 8. I had to move the decimal this way 8 times. So 2.0 times 10 to the 8th power. For me, I don't care if you put a 0.0. I'm okay with if you put 2 times 10 to the 0 power, 2 times 10 to the first power, 2 times 10 to the 8th power. I'm okay with that as well. They're the same thing. Okay. Next practice problem's over here. Now it says, what if your number is less than 1? Then your exponent is going to be a negative value. So again, I cannot have a 0 to the left of the decimal over here. So in this case, then I have to move the decimal. Which direction am I going to move it? I'm going to move it this direction. So the decimal can be to the left of the number 2. So let's move it over 1 place. So 2.0, or leave that part off, either way, times 10 to the, how many places did I move it? I moved it 1 place. But again, my number is less than 0, so it's a negative 1 power. Move this one. It has to be over here to this side, my decimal. So it's 1, 2, 3, 4, 5 places. 2 times 10 to the negative 5th power. It says here, now if the following numbers is in scientific notation, then make it into what we call a normal number or standard form. Okay? So normally we call them standard forms. This would be a standard form number. If it's not in scientific notation, well then fix it so that it is in scientific notation. All right, so let's go ahead and do a couple of practice problems. This is not in scientific notation. This is what we call standard form. So let's go ahead and I'm going to say the normal numbers, just so that way, because you're going to see the word standard form on the quiz and test. Okay, so I thought I should put that over there. A normal number is going to be standard form. Okay, so this one is a normal number. Let's go ahead and put this into scientific notation. I'm going to move the decimal. Where do I need to do? Move it to the left of the first number. So 1, 2. It's going to stop right there. So 2.3. I can't get rid of that 3. I got to keep it. Times 10 to the 1, 2. Remember, this number is less than 1, so it's a negative 2 power. This one is in scientific notation, so yes, it is okay. If it's not, then it says fix it if it's wrong. So that way it is. But yes, it is okay. This number, is this number okay? No, this number right here is not okay. The problem is it says 23 times 10 to the 5th power. So no, it needs to be 2.3 times 10 to the 5th power. Now we got a good scientific notation number. The next one needs to be put into standard form. Well, my decimal's over here at the end. I'm going to move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? 1.23 Now, traditionally, even though all of those numbers are there, traditionally we normally stop about 2. Some teachers like to go 3 digits behind the decimal, maybe even 4. I'm okay with 2 digits. If you go ahead and put the next 4, that's okay. Not a problem. Times 10 to the, how many times did I move it? I moved it over 3, 6, 9, 10, 11, 12. And that's going to be a positive 12 exponent because my number is greater than 1. Let's go again. This number is not acceptable. It says 10. So 1.0 times 10 to the 6th power. Is this an acceptable scientific notation number? Yes, it is. The next one, is it acceptable scientific notation number? Yes, it is. And this one is not in scientific notation. Okay, we're going to be dealing with numbers like this. And because these numbers are just so long, okay, we're not going to write out all the zeros. We're going to put it into scientific notation. The decimal has to move this direction. Where is it going to go? It's going to go behind the 9. Only one number can go to the left of the decimal. Now I need to count over how many places. So I know it's going to be 9.11 times 10 to the, well, I also know that this number is less than 1. So it's going to be a negative exponent. Now let's go ahead and count over how many places it's going to move. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Not done yet. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Now that's an acceptable scientific notation number. Okay, so that was our scientific notation part here. Let's go ahead and go to the next topic. The next topic is we're going to discuss accuracy and precision. Okay, normally, it says here, is there a difference between accuracy and precision? Yes, there is. Absolutely. Traditionally, most people use the word accurate or precise as if they're the same thing, as if they mean the same thing, but they don't. In science class, those two words can mean completely two different things, and it does make a difference on which word you're using. Okay, so accuracy. When it comes to accuracy, the definition is how close your measurements is to the true value. There it is. Okay? To the actual true value. The word precision is how close data, and we're saying data points. We don't literally mean like a dot, a point. Okay? Data in general are to one another. Okay? So when it comes to accuracy and precision, the difference is accuracy is the correct value. Okay? And precision, we're talking about closeness. Okay, reproducibility. How good are you to be able to reproduce the same answer again? Let me go ahead. Closeness or reproducibility. Okay, being able to reproduce the number again and again and again, whether it's the right number or whether it's the wrong number. And that's where a lot of people use those words as if they mean the same thing, and they don't. Accuracy is the correct right number. Precision does not care whether or not it's the right number or the wrong number. It's just the fact that those numbers are all going to be the same, or the closeness. Like you're getting the same value every single time over and over and over. They might be wrong, but then you're still precise. Okay, so it says, let's go ahead and look down here at these darts and look at the examples down here. For an example here, I can see how close, they are touching each other. So this target is precise and not accurate. This one is accurate and it's not a good precision, not like this, because they're not even touching. It's kind of precise. But when it comes to accurate, this one halfway is touching in it. This one is in it. This one and this one are actually touching the outer edge of the bullseye. So overall, it's okay accurate and it's okay precise, but not very good. This one though over here is actually very accurate and precise. Now the next question here says, draw what a target would look like if the person is neither accurate nor precise, right? So that would be like all over the board. If they're not even accurate, then we probably wouldn't even have one inside. Maybe close, and one over here, and one over here, and one this way, but it's all over. Maybe one way over here. But they're not accurate, they're not precise. When it comes to accuracy and precision, the key thing that we do need to know when it comes to this is that majority rules. Okay? Majority rules. And that's important. So for an example, if you got data and you've got 5 data numbers, okay, the majority is going to win. Okay? Let's keep going, because sometimes that's a little difficult to go through. We'll come back to that soon on our homework. The next one here is, we've already talked about one equation, which was density. This is another equation. Yes, it's on your formula chart. So if you haven't printed out your formula chart, you might want to go ahead and do that. Okay, we're going to go ahead and look at the word percent error. Okay, percent error. Percent error is, the measure of how accurate a value is. Okay? Kind of like, well, wow, you're 90% accurate. Wow, you're 100% accurate. You're 78% accurate. That's what this equation is telling me. Now let's look at this equation, because the equation is percent error equals the actual value minus the measured value. Okay, you're going to get a number at the top. You're going to divide it by the actual value. Okay, so go ahead and write down that equation for percent error. We have a few practice problems. It says over here, Jeannie massed a 100-gram object. Okay. Now, her first measurement was actually 175.6 grams. That's a big difference from 100. Okay. Her second measurement was 175.3 grams. Calculate her percent error for both measurements. Okay, so let's do the first one and then let's do the second one. So in this case, we're going to go ahead and get percent error equals the actual, what is the actual mass of that object? 100 grams. At this moment, we don't care about SI units, not at all. Minus, what does she measure? 175.6 grams. We're going to get a number and we're going to divide it by 100. Now, because this is a percent, I should have put over here, so let's go back. We're going to multiply by 100 at the end. So we can convert this number, that's a decimal, to a percentage. All right, so once we get this part right here, we're going to get this number and we're going to multiply it by 100. So let's get this done. 100 take away 175.6 is a negative 175.6 over 100. Multiply it by 100. Anytime you get a negative value here, just like the SI units, we're going to ignore the negative value. Okay? So ignore the negative value. 175 to 0.6 divided by 100 times it by 100 comes out to 75.6%. And there goes my answer. Let's practice again. Now she measures the same object, that's 100 grams, because we know what it is, and she gets 175.3. Well, actually, that's pretty close to the other one. Not bad at all, but she's way off. Something's fishy here. Let's go ahead and find her percent error. Equals actual value of 100 minus the measured value of 175.3. We're going to get a number. We're going to divide it by the actual value, which so happens to be 100, and multiply all of this by 100. Okay, so again, when we get a negative value, we're going to ignore the negatives, just like we ignore the SI units. Divided by 100 times 100 comes out to 75.3%. Okay. Not too bad, hopefully. Which measurement was more accurate? Well, 75.6% or 75.3%? We want to get all the way to 100%. That's the best. Okay? So for her, I'm so sorry. We want the smaller value, less than 100, because we want to get closer down to the zero, as in the error. I was thinking accurate. The error part, we don't want to be 100% error, 100% wrong. We want to be the least wrong as possible. So which number would be the least wrong? This one. Measurement number 2. Okay. So one more time, percent error. I'm sorry I misspoken earlier. 100% error would be bad. That would be horrible. We don't want to be 100% wrong. We want to be as close to 0% value wrong. We want to get closer to 0. Okay. Were her measurements accurate, precise, or neither? Well, when we look at her 2, because she just did 2, not a problem, but we definitely know that the accurate value or true value was 100. She definitely wasn't at 100. She was precise and not accurate. Okay? Let's keep looking. It says here, look at the data table to the right. Which student's data is the most accurate? Which is the most precise? Well, if we want to know the accurate, then we've got to know the true value. So the real density of sugar or sucrose is 159 grams per centimeter cubed. This is the true value. Now, which one was it, student A, B, or C, who was the closest to 159? 154, 160, 157, 157, not bad. 1.40, 1.68, 1.45, 1.51, kind of all over the board. And not even that close to here. Look, this number goes all the way to the 100th spot. So we want to get as close to that number as possible. 170, 169, 171, 170. If I had to make a call here, this would be student A. Is the most accurate. I'm not saying that student A is accurate, just saying the most accurate. Which one is the most precise? Meaning that they were able to get the values the same every single time or closer to each other. Look at this one. this number and this number are the same, but this number and this number is the same. Oops, grams was missing. Okay, now let's go ahead and look over here. 157. I'm not even caring right now about the true value. I'm just looking at those numbers, okay, on precision. Has nothing to do with accuracy. All right, so 1.54 is a difference of 0.03 away from here. 1.60, 57, 58, 59, 60, oops, let me see, 54, 5, 6, 57, would be 0.03. So trial A here was 0.03 less than those two. Trial 2 for student A was 0.03 above. Now let's look at this one. 1.70, 1.70. Okay, we want to have them as close as possible. 1.71. That is 0.01 off. Okay, we want it to be as close to here as possible. 0.69. 0.69 is 0.01 off. That's one below and one above. So now looking and analyzing the data, I can see that student C is the most precise out of all the students. A was not bad, but C was better. Okay, calculate the percent error for the least accurate student by using their average measurement. Okay, so for the least accurate student, well, if we know that the most accurate was student A, who was the least accurate? The least accurate would be the one that's furthest from here, from the true value, which would definitely be student C. Look at those numbers versus those numbers. Those are a little bit closer to 0.59 versus 0.70, 0.71. Okay, so we're going to say student C is the least accurate, and they would like to know what is the average. So let's find average. 1.70, 1.69, 1.71, 1.70. We need to add all those numbers together. So let's go ahead, oops, get those numbers, add them together. This is not working too well. Okay, there we go. 1.70 plus 1.69 plus 1.71 plus 1.70 equals divided by 4, which this comes out to 6.8. I need to get this number and divide it by 4, and I get 1.7. Okay, so I found the average. So that's the value that we're going to use. That is their measured value. So let's go ahead and get the true value, which is 1.59 minus 1.70 over 1.59. And we're going to multiply this by 100. So let's go ahead and let's do our math up here. I got a negative 0.11. Ignore the negative. Divided by 1.59. And we're going to times it by 100. I get 66.92% off. 6.92% off. That's not too bad. We want to get as close to 0 as possible. That's the best. Okay? So that's not too bad at all. Let's turn the page and let's keep looking. The next part is nice because this is kind of a review of what we talked about last unit. We talked about density because we were talking about extensive and intensive properties, physical properties of an object. Okay, so let's first, when we're talking about density, there's a few things that we definitely need to know. We need to know the SI units. We already talked about this, so it's kind of a review. The units. We're going to need to know the mass of the object, which can be in grams or kilograms. Normally, traditionally, that's what we use. It can be milligrams, okay? But traditionally, those are the two. The units we're going to have is volume. So we need to know the volume of the object. And that can be in centimeters cubed. It can be in millimeters cubed. It can be in kilometers cubed. Okay? Or milliliters. Don't forget that if it's this one, that means it's a solid. If it's this one, that means a liquid. Now, when it comes to density, I'm going to come over here and put density. Those units cannot cancel each other out. So in this case, it would be something like grams per cubic centimeters or grams per milliliters, right? A solid or a liquid. Again, it could be kilograms per kilometers cubed, or it could be kilograms per milliliters cubed. Milliliters, I'm sorry, I didn't mean to say cubed. Let's keep going. Volume. You learned this word already long time ago. It is how much space an object takes up. Now we know that solids, if we're looking for solids, you've done this before, length times width times height. And it equals, for an example, centimeters cubed, millimeters cubed, kilometers cubed. Liquids, how do we find the volume of an object that's a liquid? Well, we're going to put it into a graduated cylinder. Okay? Now, when we put it into the graduated cylinder, if it's just a regular liquid that we're looking for, we're going to put it in there. But if it's what we call a solid that has an irregular shape, then we're going to do something a little different. We call it water displacement. And we saw that in our little lab that we did on the computer. Every time you put the cube in it, and when the cube sunk to the bottom, the water level went up. So we're going to talk about that in just a moment. Now, I also know that you've talked about this word before, meniscus. And don't forget, meniscus is the bottom of curve. Okay? On a graduated cylinder. Now, the reason why a meniscus occurs is because it's due to the adhesion and cohesion of the H2O molecules. The way that they suck to each other and pull and suck on each other and grab onto each other, the molecules, that we call that adhesion and cohesion. Okay, and that's the reason why it occurs, if you're wondering why. Now let's go ahead and look at the word mass. Again, a review word for you. How much matter